Okay, example 10, graphing a cosecant graph. Again, our goal is to get that a plus b, and this is going to be cosecant of c parentheses x minus d. Again, always go back to this type of structure. I keep writing it down. If you feel that necessary to write it down to remember it, maybe just have your notes out while you're looking at the problem. It doesn't matter what the trig function is, they all have the same basic structure to establish these values. This is not in that structure yet because there's a number in front of x, and again there's no a value, so if I start off going y equals 0 plus 2 cosecant, I'm going to factor out that 2, and that gets me to here. And I can see that a is equal to 0, b is equal to 2. All right. Cosecant comes from sine, it's reciprocal sine, right? So I'm going to be thinking in my head for sine, it starts at 0, positive goes up, 0, down, 0. That's the normal layout of sine graph, right? We're doing cosecant though, so the zeros become asymptotes. So I can establish the layout of my stuff. So I'm going to have 5 dashes on this altogether. The phase shift is going to be the origin dash, and then the 4 dashes that we normally put for sine or cosine, right? So the first dash, or the first of the 5 dashes, we're going to start at an asymptote, hit the high number, asymptote, low number, asymptote. So that's the layout of the points at least. The other thing I can see here, of course, c is equal to 2, which means the period is going to be 2 pi over 2, better known as pi. And that means per dash is going to be pi over 4. And my phase shift d is equal to positive pi over 2. Now just for the sake of doing this correctly, and because again there will be times when you have to put the dashes marked, I'm going to mark the dashes on this one. And it's real simple. If you take d and the per dash and make them have a common denominator, all right, d is our starting point. So common denominator pi over 2 and pi over 4 is 4, right? So pi over 2 is the same as 2 pi over 4. That's my starting point. And then I simply take the per dash and keep adding that much in common denominator world, right? So 2 pi over 4 plus pi over 4 is 3 pi over 4. 3 pi over 4 plus pi over 4 is 4 pi over 4. Plus pi over 4 is 5 pi over 4. Plus pi over 4 is 6 pi over 4. It's real simple. Just keep adding pi over 4 in a common denominator situation. It's real simple to do. Just keep on adding the top number and you're good to go. And then if you see they reduce them. So those 3 reduce. I would do this somewhere, okay, before I put them onto the graph. So just kind of establish what they should be, and then you can put them on the graph where they belong. All right. Once again, we're starting in the positive region off to the right a little bit. So if I put my y-axis way over here to the left, maybe use a blue line that's not dashed, that would be kind of nice. Kind of keeping with the theme of the current x-axis. All right. So my y-axis is there. I don't know why. There we go. Y-axis there. Our center line is 0, and we're going 2 spaces up and 2 spaces down. Again, with secant and cosecant, you've been going up to infinity, down to negative infinity. So don't go way up there. Go up a little bit and make sure there's some graph space above there to allow the graph to flow up to positive negative infinity. I'm starting at pi over 2, positive pi over 2, so I'm going to put a little break here. Again, nothing really interesting happens between 0 and pi over 2, so I can just leave those out. I mean, honestly, it would be 2 dashes to get to pi over 2. Pi over 4, 2 pi over 4, right? And so it wouldn't hurt to put an extra dash that represents pi over 4. But again, I'm just going to cut the graph. I tend to do that usually. So my starting point is pi over 2. And then I've got 4 dashes after that, somewhat equally spaced. Again, you don't have to get perfect, but get close enough that it looks like they're somewhat equally spaced. And going back to what I said yesterday, I do want to put the labels that label the dashes, but I can graph all these things before I label the dashes. That way, if I can see where the things are going to be, so I might need to move something out of the way. In fact, it might be better not to write the pi over 2 yet. I started an asymptote, so if I go ahead and graph that first, there's an asymptote the third dash and an asymptote at the last dash. I got really bad. Let's see. You of course can put a straight edge down on your paper and get right where you belong. All right, and then we hit a top. B is positive 2, so the top is positive 2, the bottom is negative 2, thinking back to the sine and cosine. So if I was doing a sine graph, you can see the sine graph, the reciprocal, that asymptote's at zeros, and it's going to go like this everywhere else. And here then I can put pi over 2 kind of over to the side a little bit so it's not getting destroyed by that asymptote. Next is 3 pi over 4 doesn't reduce. 4 pi over 4 is next, which is pi. You can slide that right next to the asymptote. 5 pi over 4 doesn't reduce. And then 6 pi over 4 would be 3 pi over 2 would be my ending point. And just like yesterday, we have the ability to check this with a calculator. If I was to graph 2 cosecant, I'd probably go ahead and type it in like this. The calculator doesn't need that 2 factored out. If I typed in 2 sine of 2x minus pi, end parentheses to finish the sine function and hit the -1 to reciprocate, that's now cosecant. I'm in radian world, right? I'm going to change my window. I'm going to start at pi over 2, end at 3 pi over 2. And if I want to go up by pi over 4s, I sure can. The scale's not that important. As far as min and max, again, they're going up and down to positive and negative infinity, so maybe -10 to 10 would be probably good to see. Again, there's nothing special about those numbers. I'm going to go at a 2 scale because that gives me an idea there. So there's the first one, and there's the second one. And you can see if I were to graph y equals 2 and -2. Use dash lines for those. Use both dash. You can see that the bottom point and the top point are where they should be based on what we're looking at there. So again, you can always verify, once you get your graph drawn, if you get the x scale and the y scale similar to what you have on your paper, what you see on your screen should match what you have on your paper. Okay. It won't draw the asymptotes, but other than that, it should have the graph you're looking at. So you can always verify that way.